Welcome back, 3.1, part 4. I think we can wrap it up with this section, but I know that some of the functions are getting a little tougher in our examples, so hang in there. This is one of the bigger sections out of all the material. So our topic here is absolute maxima and minima, plural of maximum and minimum. The one single highest or lowest point for a function, if it even exists. So this kind of question is often asked over a restricted domain. Rather than using the entire x-axis, we are often given a finite interval to consider. When we do have a finite interval, then sometimes an endpoint can be higher or lower than any critical points. The only way to know if this is the case without a graph is to compare y values. So before we even get though to that, let's look at some graphs. So the difference is, if I look at this function here, this graph with my arrowheads on each end, we've got a relative max, we've got a relative min, but no absolute max or min. Because of those arrowheads, this graph does not have a single highest point. But what if I look at a truncated version, a cut-off version of this graph, where I start at a certain point, I still go up and down and go back up again, right? We still have the relative max and min we had before, but now look at this. The endpoint is now an absolute max. It is the highest point on this graph if I'm not allowing the graph to go on forever. And the left endpoint in this particular graph happened to be an absolute min. And the only way to know that this right-hand endpoint was the high point is because it's higher. You can see it. It's the y value is going to be higher than the y value of the relative max. And the same for the absolute min. The y value is what tells you how low to put the point. So that's where we're going to compare the y values. So here's the two-step process. And again, this is for absolute max min stuff. So you're still going to solve your first derivative equal to 0. And then none of that sign chart stuff. You're simply going to compare y values at the critical values and at the endpoints. And I usually just say make an xy table to do so. So here's an easier example, and then we'll do a harder example, and then one more example to hopefully wrap up. So number 48, find, if they exist, the absolute max and mins for this function f of x equals x cubed minus 3x squared minus 7 on the interval 0 to 5. So remember, this is telling us that this is x equals 0 as our left endpoint, and then x equals 5 is the right endpoint. We're going to start at 0, end at 5, not consider anything past that. So let's start with the derivative, f prime of x. From the derivative from x cubed, I get 3x squared. In the middle, minus 3x squared, we get the 2 comes down, we get minus 6x, and the 7 goes away. So I'm going to set that equal to 0, look for the usual common factor, 3x in this case, leaving the other x minus a 2 equals 0. So it looks like from 3x equals 0, I get x equals 0. And from x minus 2 equals 0, I get x equals 2. Those are both in the interval. 0 is just barely in there. We have a closed bracket, so 0 is part of it. And then 5 is the other endpoint. So here's my table. I'm going to plug in both of these values, 0 and 2, and also include the other endpoint. So it's the critical values and the endpoints. So 5 is an endpoint only, 2 is a critical value, and then 0 is an endpoint and a critical value. It's both of those. So it's doubly important. And then where do we get y values from? We get y values from the original function. The derivative gives us slope, but now we want y values. So I'm going to go ahead and plug in 0. That one's easy. I get -7. When I plug in 2, let's see, I can't do that really fast. I got -11. And then plugging in 5, I got 43. So what we have here are 3 points, and you may be able to know what you're looking at here just by looking at these numbers. But if it's not clear, let's make a quick graph. 0 is down here at -7, 0, -7. And then by the time we get to 2, we're down here at -11. And then by the time we get out to 5, we're way up at +43. So again, we're just getting coordinates, the y coordinates. So if we were to connect these dots, I can see that 2 ends up being my absolute min to -11. And then 5, 43 ends up being the absolute max. And then 0, 7, we're not asked about it, but that would just be a relative max. Not so important for us in this particular problem. So hopefully that kind of makes sense. If that makes sense, then you're in a really good place, that you find your critical values and then you just compare critical values and endpoints in an XY table. Now we are going to go ahead to a little bit harder problem, one of those rational things. So let's see what we can do with it. So this is similar to number 49, which is in your homework. Find, if they exist, the absolute max mins, there's that word absolute again, for f of x equals 1 over x minus 2 on the interval. This time it's a little bit different. We're starting at 4 and going off forever. So the domain of that we're considering is a closed circle at 4, and then we're going off to the right. And you may or may not have any idea what this graph looks like. And again, we're learning how to look at derivatives and get this information. So let's rewrite this, maybe with a negative exponent, x minus 2 to the -1. So we can take the derivative. Suppose we could use the quotient rule tool, but it's a lot faster this way. So the -1 comes down, times x minus 2 to the -2. There's a little detail in here, if you know about the chain rule, that fortunately doesn't change anything if you use it or not, and you're supposed to. So we'll just let it go. But I can rewrite this as -1 over that quantity x minus 2 all squared. Now, we want to set this equal to 0, but there's a really useful fact about fractions. We know they're undefined when the bottom number is equal to 0, but when is a fraction actually equal to 0? It's equal to 0 if the top is equal to 0. I'm going to write that down. So here's what I wrote, a fact. A fraction is equal to 0 only when the numerator, the top, is equal to 0. I have to say, while I'm working on this video, I'm looking out in my backyard and there's the most beautiful swallowtail butterfly flying around, one of those big yellow and black ones. Absolutely stunning. And if I drift away, that's because I'm watching the butterfly. But in any case, so looking at our fraction, we're trying to solve 1 over x minus 2 all squared equal to 0. This top part, -1, is not equal to 0, ever. It cannot ever be equal to 0. So this equation has no solution. When we set this fraction equal to 0, there is no solution. So no critical values. So what are we going to do for our XY table? Well, 4 is an endpoint there, and then we don't have a right endpoint. We've got a left endpoint. So let's at least put x, f of x, make our table. So we can put the 4 in as an endpoint. And then I have to know what this function is doing. So let's try maybe 1 or 2 points beyond that and just see what happens. You might be able to think about, oh, the fact that we're squaring on the bottom means positive, and the negative on the top, what does that mean about the sign of this derivative? Think about that for a moment. See if you can jump ahead. Otherwise, just plug in to the original function. So again, f of x, which is the original 1 over x minus 2, If I plug in a 4, I get 1 over 2, or 1/2, or 0.5. If I plug in 5, I get 1 over 3. It's about 0.3 or so, approximately. If I plug in a 6, I get 1 over 4, which is 0.25. Aha! I can see that f is decreasing. And we could make the note that f prime of x is in fact less than 0 for all x greater than or equal to 4. And that's again because we've got a negative on top and a squared piece on the bottom, which will be positive, as long as we're not dividing by 0, which we're not. So we've got a negative derivative, which means that f is decreasing. And I'm going to write that down. So since f is always decreasing, that derivative is negative, we must have an absolute max at that starting point for this interval, 4, 1/2. So that's how we answer that. So again, I totally get that that's quite a few notches above the first example. So work hard. If you can get the first example pretty solid, then come back and study this example again. I usually go somewhere kind of in between for the actual exam. All right, let's see. Looking at the time. Oh, one more example. Let's at least get through part A. So the function p of t equals 30t over t squared plus 16 for t greater than 1 relates the population p in millions of bacteria in a culture to the time t in days after a particular slow-acting toxin is introduced into the culture. So letter A, determine the number of days after the introduction that the population of bacteria will be at its maximum. So as soon as I see that word maximum, that tells me to solve the derivative equal to 0. So I'm actually going to pause my recording to keep it in the time limit. I'm going to work on the quotient rule to work on the derivative. So here I've set up my quotient rule, and I'm going to keep working on it. And here's my derivative of 30t being 30. Derivative of t squared plus 16 is 2t. I've distributed and combined like terms, and I have negative 30t squared plus 480 all over t squared plus 16 all squared. And now, from our comments before, as I go to set this equal to 0, it's enough to focus on the top part being equal to 0. So I'm going to work on that. So I apologized for going through this quickly, but I don't want to go into a whole other part of the video. So solving the top part equal to 0, and subtracting over the 480, dividing, I get t squared equals 16, which has two solutions, t equals 4 and t equals negative 4. But remember that we were told that t had to be greater than 1, because we're talking about a number of days. So t equals 4. The max occurs at t equals 4 days in particular. All right. Now for part B, provide a mathematical argument to demonstrate that once the population is at its maximum, it will only decrease to 0. That could be decreasing. We know that that's first derivative less than 0. So we can look at our first derivative and talk about whether this is positive or negative. In particular, notice the bottom is squared, so it's always positive. The top, I'm going to do a little factoring, common factor. I'm going to take out a negative 30, and I get t squared minus 16, which does factor into t plus 4, t minus 4. And then I can make a little sign chart. And I'm just going to squish this in here. And so know that this is not that important to get. But as I work on this, I will get that this is going to be negative followed by positive followed by negative. So in particular, we're asked once the population is at the max, which we know occurs at 4, then the derivative is less than 0, so f itself is decreasing. So super fast, but we are out of time. Hopefully we can talk about it soon. See ya.